Swayam Prabha. Digital India. Educated India.
Good morning. Welcome to the Fluid Mechanics course. We are in the subject solutions of Navier-Stokes equations. In fact, we have already discussed the exact solutions of Navier-Stokes equations, and we have also discussed a couple of approximate solutions of Navier-Stokes equations, in which we have also discussed the boundary layer theory, which is a very important concept of fluid mechanics. Today, we will be talking about the boundary layer thickness. In the last lecture, we have already discussed the boundary layer thickness, where the velocity is expected to be the uniform, the free stream velocity. The location where the free stream velocity is going to be achieved from the boundary, that distance is your boundary layer thickness, and that is going to be achieved where y tends towards infinity. Now, obviously, we cannot really take that infinity as a practical consideration. It is customary to select the boundary layer thickness as delta as that point where u by u, or the normalized velocity, approaches 0.99, or the velocity from the boundary once we start measuring where it is approaching 0.99 u, the free stream velocity, we consider that distance as our boundary layer thickness. Alright, and based on the Blassius solution, we have already seen that u by u reaches 0.99 for a value of eta equals to 5.0. Eta is what? Y by delta. So we know the y is the distance from the bottom plate towards the boundary layer. So y by delta, delta is the boundary layer thickness, y by delta equals to 5 is going to give us the value of u by u equals to 0.99. Now, based on that, we could write down delta divided by y, or we could write down delta equals to 5x divided by root over rex. X is the distance of the plate. So from the leading edge of the plate to distance x, if we are measuring what is the boundary layer thickness, then it is going to be 5x divided by square root of rex, and rex is nothing but your Reynolds number, okay, at distance x. Now, although we have discussed that to find out the velocity where it is 0.99, it is very difficult to ascertain where that 99% of the velocity is achieved. It is quite cumbersome to find out exact location from the experiments. Okay, so that's why there are different terms which are used to identify this boundary layer thickness. How we are identifying? The definition what we have said above for the boundary layer thickness is somewhat arbitrary, and a physically more meaningful measure that is used for estimation is called displacement thickness. What is that displacement thickness? We will try to understand as we move on with the lecture, but at least now we understood that there is a boundary layer thickness where eta is equals to 5, and we cannot really measure that so easily, so we have coined some other concept which is called displacement thickness, and with that we will be able to correlate to boundary layer thickness, and we will be able to get the value. So now let us see what is that in the due course of this lecture. In the previous lectures, you have already seen that we calculated the drag on flat plate. So in linear momentum principle, we applied that concept and we calculated the drag on a flat plate. Here also we are calculating the forces or the shear on the flat plate using this boundary layer concept. If you remember, in the previous lectures, we did not account for this boundary layer. What we said, if we take a control volume and understand what is the flux coming in and coming out, then we can find out what is the force. But we know that the force is being generated or force is exerted due to the drag on the plate, and that is nothing but the shear, due to the shear on the plate. And the shear is going to act by the shear stress that is known to us by Newton's law of viscosity. Tau is equals to mu into du by dy. So that du by dy is coming in picture within the boundary layer. Outside the boundary layer, what happens? What is the du by dy? We have already discussed that the du by dy is going to be 0 because we assume that it has reached almost free stream velocity and u is going to be uniform above this boundary layer. So du by dy is going to be 0. So shear stress is 0. So that means the force that is actually being exerted on the plate is due to the boundary layer, and that we did not consider in our linear momentum principle, but still we could solve it applying the concept because we are trying to understand the flux coming in and flux going out. But now I'm not going to explain the whole steps. We have already seen that. Just to give a recapture of the concept that we discussed, I'm just showing it. All right. So based on these concepts, where we found that the surface through surface AB there is a mass inflow, through CD there is a mass outflow, and again there is a mass outflow or mass leaving through the surface BC. So when we considered all this and calculated the outflow momentum minus inflow momentum, we could finally derive the drag force, and from drag force we could also derive what is the shear, that is tau 0 shear stress along the wall of the plate, okay, or the plate surface. Okay, so this is what we could derive. Now taking that as a precursor, let us now understand what is happening within the boundary layer. We have already seen the Prandtl's boundary layer theory and the equations. So now looking at an expression which is suggested by Prandtl, a velocity distribution was considered. Okay, so we have said already u by u is a function of y by delta. If u by u is a function of y by delta, then or function of eta, then here the value function of eta is written as 3 by 2 eta minus eta q by 2. This is an expression or velocity distribution which is assumed by Prandtl, considering that this could be the profile. Obviously, a lot of research and analysis has gone inside, and finally this kind of expression was suggested. So what we are looking at is the expression that was considered by Prandtl. So finally we can see that u by u is equals to 3 by 2 eta. Eta is, please remember, eta is nothing but your y by delta. Okay, so 3 by 2 eta minus eta q by 2. For this, we also could write that f of eta equals to 1. Now that is applicable, f of eta equals to 1, where? Because y by delta is going to be 1 when y is greater than delta. Now within this 0 to delta, within the surface of the plate till the boundary layer thickness, the expression is going to be this. Okay, so we have already eta equals to y by delta. We can write down dy is equals to delta d eta. Okay, now let us assume the profile to satisfy the boundary conditions. Now what are the boundary conditions? The assumed profile must satisfy the boundary conditions, and the boundary conditions we know that the velocities are 0. So based on that we can write down our boundary conditions, and it has to be satisfied by this expression or the equation. So using the assumed profile that we have already derived or we have written, we can write down the expression for shear stress. In the previous slide you have seen the shear stress we have written based on the linear momentum principle, but now if we write down, we will be able to write down tau 0 is equals to rho u square dou by dou x delta. Basically we are substituting the value of u in this expression, and dy is being substituted as delta d eta. Okay, so by substituting all this we could write down this expression, and then just rephrasing that, if you see, we substituted the value of u, small u, as and when required, and then taken the capital U out. So here we have multiplied by u square, so that has gone out. Now this is our new expression. All right. So by solving it, you could finally write down tau 0 is equals to rho u square 0.139, which is kind of a coefficient which has come out, multiplied by dou delta by dou x. Okay, so this is your expression for shear on the plate. Okay, now to find out the value of delta and tau 0 in terms of some known quantities at the boundary, what we can do, we can adopt the Newton's law. Newton's law is known to you, that is nothing but your tau is equals to mu du by dy, and here we are finding out at y equals to 0 or on the surface of the plate. Now if you substitute the value of du by dy, you can write down mu u by delta dou f by dou eta. F is the function, dou f by dou eta, and here again y by delta we are substituting, so eta is also going to be equals to 0 at the boundary. Okay, so now solving this, if we write down, we will get this expression, and that is going to give you 3 by 2 mu u by delta. Now equating this expression which you have derived, okay, for the above equation that we already derived for tau, that is with a coefficient of 0.139, we could write down 3 by 2 mu u by delta is equals to rho u square 0.319 dou delta by dou x. Now simplifying this, we can write down delta into dou delta, delta d delta is equals to 10.78, which is a coefficient which has been derived from this, multiplied by mu rho u dx. Okay, so this expression now is easy to solve. We can integrate and write down delta square by 2 is equals to 10.78 nu by u, rho by mu by rho is nothing but your nu by u multiplied by x plus a constant. Okay, so here the moment we have a constant, it is time to apply the boundary condition. What is the boundary condition? We already know the delta or y by delta is going to be 0. So for x equals to 0, delta equals to 0. All right. So if we apply that boundary condition, we can straight away get constant is equals to 0. Now substituting the value of constant equals to 0, we have only this expression, and if you simplify this expression, you will get the value of delta, which is nothing but 4.65 square root nu x by u. Okay, so just again further simplification, if you multiply x on both sides, you can write, divide by x on both sides, you can write delta by x is equals to 4.65 divided by square root rex. If you remember, now based on this assumption or assumed velocity profile that we have taken, we could write down delta by x is equals to 4.65 divided by rex. Based on the Blasius solution, what we had got, eta equals to 5. So we could also write down there that delta by x is equals to 5 divided by square root rex. So here, by assuming this profile, okay, this approximation of the profile, we could write down, or we could get 4.65 divided by rex, square root rex, and there it was 5. Okay, so they are very much closer. Now Blasius developed the expression which was without these approximations, but then Prandtl's approximate profile has given rise to this 4.65 divided by square root rex. And using this, if we evaluate the value of tau, that's the shear stress, we can get an expression that is going to be 0.322 mu u multiplied by square root u by nu x. Okay, so this expression we could get based on the assumed velocity profile. Now, similarly, we can also find out the value of d, which is the drag force. What is drag force? The shear stress acting over an area. Now, if we take unit width and we integrate over 0 to L, it's the length. So, per unit width over a length, the force that is going to act is d, and that can be obtained by integrating tau over 0 to L, and that will give us 0.644 square root mu u to the power 3 L. Okay, so or you can write down square root of rho u, yes, square root of rho u, then u to the power 3 by 2 L to the power 1 by 2. Okay, so this is the expression we got, and the coefficients that we could get for the tau 0 and d are 0.332 and 0.664. Okay, now the drag per unit width we can write down as d equals to cd. This is a standard expression. Half cd rho u square is the drag force, and per unit width over a length it is going to be cd rho u square by 2 multiplied by L, length. Okay, so with this expression we can now find out the value of cd. We have a d here and we have a d here. By equating these two, we can write down, or we can find out what is the value of cd. The value of cd is going to be 1.328 square root rel. Why L? Earlier we used to tell x, but here we are finding out that force or the drag on the total plate, which is an average drag, and that is going to be obtained based on square root rel. If you are finding out the drag force up to certain length, let us say x, then it is going to be rex. Okay, so the length that you consider is going to drive this. All right, now let us look at slightly different type of velocity formulation or velocity profile and see what is happening. What we have considered in this case is 3 by 2 eta minus eta q by 2. So that is the velocity profile we have considered. But now if we simplify that, if we try to oversimplify the distribution, velocity distribution, and take f is equals to u by u is equals to y by delta or eta, which is a linear profile. If we assume that and substitute that in our derivations, we can write down, we will get a coefficient of 0.1666 or 166. Okay, so with this we can also write down the beta, that is dou f by dou eta equals to 1, and taking all this, if we derive, we'll get an expression that is delta by x is equals to this one. Okay, so that is square root 2 multiplied by 1 divided by 0.166 multiplied by 1 by square root re, and by simplifying all this we can straight away write down delta by x equals to 3.47 divided by square root re or rex. Okay, so the earlier velocity profile gave us a different value, and this velocity profile is giving us another value. So it depends on the velocity profile that we assume in the beginning and derive the solution. So assumption of velocity profile is very, very important, and for different velocity profiles we may get a different boundary layer thickness. So overall, the expression that was given by Blasius, that is delta by x equals to 5.0 divided by root over rex, is still well accepted and valid. Okay, so now having discussed this, let us quickly look at an example problem. So this example problem says a smooth flat plate 2.5 meter wide and 0.75 meter long, parallel to the flow direction. So plate is parallel to the flow direction. Okay, there is no inclination of the plate or anything, it is parallel, is held in water at 65 degrees Fahrenheit temperature, where the kinematic viscosity is, or the nu, is equals to 1 centi-Stoke following an undisturbed velocity of 0.6 meter per second. The question is, determine the thickness of boundary layer and the wall shear stress at the middle of the plate and at the trailing edge of the plate. Also find the total drag force experienced on each side of the plate or one side of the plate. Assume the boundary layer as laminar over the entire length of the plate. Okay, so the boundary layer can be laminar and after some time it could be turbulent. Okay, but what we are assuming that this whole length of the plate, the boundary layer remains laminar. So the concept that we have discussed so far, the laminar boundary layer theory, we can apply here. Okay, now in this, let us look at the solution. You have already shown the plate here. This is the plate and we have 2.5 meter wide. So please remember that the moment we are telling 2.5 meter wide or width, so that is across the direction of the flow, and along the direction of the flow, which is the length, is 0.75 meter. It is not necessary that whichever is the higher length is going to be the length, not necessary. We are telling this is the flow direction, which is along this 0.75 meter length and 2.5 meter wide plate. All right. So for on this plate, you have the flow and the boundary layer is going to evolve from the leading edge of the plate and it will keep on increasing as we move downstream along the flow. Okay, and we need to find out the thickness. Where we have to find out? At the middle of the plate. So that means this is my midsection of the plate, and at this point I need to find out what is the thickness delta, and again at the trailing edge I need to find out what is the value of delta as well as all other parameters. Okay, so now we already know delta by x is equals to 5 divided by root over rex. So re is equals to ux by nu. Nu is nothing but your mu by rho. So all these things are known to us. What are the parameters that are given to us? We already have length, that is 0.75 meter, width 2.5 meter, u is the velocity of the flow, that is given as 0.6 meter per second, nu, that is kinematic viscosity, which is given as 1 centi-Stokes, that is equals to 10 to the power minus 6 meter square per second. So it is better to write all this in the SI units and then start solving so that you don't do mistakes. Okay, now let us find out what is going to happen at the midsection. We have to find out the value of boundary layer thickness at the middle of the plate. Okay, what is that at the middle of the plate? What is your length or x is going to be 0.375 meter, half of the total length. So for that, if we substitute the expression, that is delta by x equals to 5 by re, we can write down 5 divided by re, this is your expression for re, u x divided by nu multiplied by x, the x that was here has come up here. Now by substituting all the values, we could write down the boundary layer thickness is going to be 3.95 millimeters. Okay. Similarly, we can find out the value at the trailing edge. At L equals to 0.75, delta is going to be equals to 5.59 mm. So you can see how the boundary layer thickness is increasing. Similarly, we can now solve for the shear stress. So shear stress at the middle of the plate is going to be this expression which we have already derived, 0.332 mu u square root u by nu x, and we all know the values of these parameters. It is just matter of substituting the values. If you substitute all the values, you are going to get 0.252 Newton per square meter. Okay, so here please understand mu is equals to nu multiplied by rho. Okay, so the mu value what we are using here is nothing but nu multiplied by rho. Okay, rho is known to you. What is the rho of water is 1000 kg per meter cube. Okay, so by taking it, we can also find out the shear stress at the trailing edge at L equals to 0.75 meter. The same way, if we calculate, we'll get shear stress equals to 0.176 Newton per square meter. Okay. So now we can find out what is the drag force. So the drag force is given as, we wrote it as D, that is 0.664 mu u to the power 3 by 2 L to the power 1 by 2 square root of nu multiplied by the width, that is B, because we derived the expression for unit width. Now for a certain amount of width you have to multiply that with the exact width so that you get the answer. Okay, so now I think here it should be mu to the power 1 by 2 based on the expression that we have derived. Okay, so anyway, by substituting all the values we could finally get a value of 0.6681 Newton. So the overall what we understood is this solutions for shear, drag and all these were arrived based on some assumptions or approximation to the Navier-Stokes equations, and using these final derivations or expressions we can find out the values of boundary layer thickness, the shear stress at the boundary as well as the drag force acting on the surface. Alright. Okay. Now having understood this, now let us look at the meaningful term which we said is the displacement thickness. See, this is all derivations we can find out from various values, but to measure experimentally to find out the boundary layer thickness we found it difficult, and we told that there is a displacement thickness which can help us to find this out. Let us try to understand that. So now looking at the displacement thickness, the displacement thickness delta star, boundary layer thickness we are talking is we are referring it as delta, displacement thickness we are referring it as delta star. Delta star is the distance that a streamline just outside the boundary layer is deflected away from the wall due to the effect of boundary layer. What does it mean? It means if you have a streamline, you have a plate and you have a streamline here, right? After the boundary layer, you have a streamline which is possibly moving like this. Now let us say this streamline is being displaced by some distance due to the effect of boundary layer. So what does it mean? It means the free stream velocity u is being displaced by this distance. So that means what is the flow that is being retarded due to the boundary layer, the effect of that is going to be felt here. Okay, now let us look at the definition in a slightly different way. This is another way of defining that. It can also be defined as the distance by which the external potential flow is displaced outwards due to the decrease in velocity in the boundary layer, or the retardation that happens within the boundary layer. Okay, or alternatively it can also be told that displacement thickness is the imaginary increase in thickness of the wall. Okay, you have the wall, or the wall thickness has increased by certain amount. There is no reduction in the velocity, rather we are telling it's a smooth surface, there is no change in the velocity profile, it is same free stream velocity, but there is an increase in the wall thickness, apparent increase of wall thickness, which is affecting the flow. Okay, so there are different ways to understand, but to understand it in more physical sense, let us look at a pictorial representation. Let us look at this figure. So what happened? You have the plate or boundaries here, the surface of the plate, and from that your boundary layer is varying up to this 0.99 u, and beyond that the variation is negligible or it's considered as uniform velocity. Now within this boundary layer, this velocity gradient is going to be seen something like parabolic within the laminar boundary layer, and there is a reduction in the flow. Here it is u is going to be 0, and as you go up, the u is going to increase and it will reach 0.99 u at some point. Okay. Now, experimentally, we cannot really pinpoint exactly this location where it is 0.99 u. So we keep on measuring at different locations what is the velocity, and we will have a profile something like this. All right. Now, from this profile, we can write down this expression. What is that? U multiplied by delta star. Delta star is the displacement thickness. So the free stream velocity multiplied by displacement thickness is equals to the integration over 0 to infinity u minus u dy. So the overall reduction in the flux is calculated here. What is the reduction? Your reduction is u minus u at any elemental strip. So your reduction here is the free stream velocity u minus the instantaneous velocity at that location small u. Okay. Now you have this u minus u, and if you integrate over this distance small strip dy, you will get the flux that has reduced or retarded within this strip, within this small elemental length dy. Okay. Now if I integrate it over 0 to infinity, then I will get the total flux that is being retarded. Okay. And that total flux, if I assume that there is no retardation, rather it is u or free stream velocity everywhere. So what would be the distance delta? Okay, what would be the distance delta star? That is the displacement thickness would be comparison to that total retardation. So to compare that, what we have done, we have written this expression u delta star equals to 0 to infinity u minus u dy, and by revising this, we can write down delta star displacement thickness equals to integration 0 to infinity 1 minus u by u dy. Okay. So practically, it is not really possible to integrate up to infinity, and we have also seen that we are not going to integrate up to infinity. We are stopping it at 0.99 u. So based on that, we can also integrate up to only delta. Okay. So but we don't know where is the delta, so you keep actually taking all the way up to the top of the flow, and you will be able to derive for the laminar plate, boundary layer flow, you can derive delta star is equals to 1.72 x divided by rex. So you can see the similarity in the expression that we derived, or the Blasius solution derived for delta, that is the boundary layer thickness, and displacement thickness that we have got. So if you look at the Blasius solution, it is 5x divided by rex, square root rex, and delta star is 1.72. So if you take the ratio, you will get almost delta is equals to 3 delta stars. So delta, or the boundary layer thickness, is 3 times larger than the displacement thickness, and by measuring the velocity profile, we can integrate this u minus u over this whole distance, and we can find out from that we can get the delta star. Multiply by 3 will give us the approximate value of the boundary layer thickness. So this is the easier way to find out from the experimental data. Okay. Now there is another thickness term which is also used in some locations, which is called momentum thickness. Momentum thickness is denoted as theta, okay, and is another measure of the boundary layer thickness. What is momentum thickness? It is defined as the loss of momentum instead of loss of flux, or u minus u we are telling. So we are telling loss of momentum in the boundary layer as compared with that of potential flow. What do you mean by potential flow? These are just to introduce new things so that you recall everything. So outside the boundary layer, we have already discussed that it behaves like a potential flow. Okay, the viscous effect is negligible, so it behaves like a potential flow. So the loss of momentum in the boundary layer as compared to the outside potential flow is considered for finding out the momentum thickness. And if we write it in mathematical way, we can write down rho u square theta is the momentum that is in the thickness, momentum thickness theta is equals to integration 0 to infinity rho u multiplied by u minus u. See, this is the retardation and reduction in the velocity, and the momentum reduction is going to be rho multiplied by u. U is the velocity at that stretch. If you multiply rho u with this velocity, then you get the momentum, and this is the momentum which has reduced, and that we are equating with this, with the theta. Okay, by solving this equation, you can write down theta equals to 0 to infinity u by u multiplied by 1 minus u by u dy, and a solution of that will give you, okay, theta equals to 0.664x divided by square root rex. Okay, so we could write down the value of theta similar to delta star. And now if you look at the ratio between theta and the boundary layer thickness, you can see delta is going to give you a coefficient 5, theta is giving you a coefficient 0.664, and the ratio is going to be 0.133. That is nothing but theta is 13.5% of the delta at any location x. Okay, so now if you find out the value of delta star and theta, which can be obtained easily, then you can find out the value of delta. Okay, so this is basically the essence of this thickness, displacement thickness and momentum thickness that we could obtain. Now let us look at a simple problem applying this displacement thickness or momentum thickness. So this is a problem which says the airstream velocity is 30 meter per second and is uniform at the entrance of a square duct. You have a duct through which the flow is passing through with a velocity of 30 meter per second and is uniform. The duct measures 80 mm by 80 mm, and at a cross section 0.3 meter downstream from the entrance, the displacement thickness on each wall measures 1 mm. Find the pressure change between the entrance and the downstream section, that is 0.3 meter downstream. Okay, you find out the pressure difference P1 minus P2. Okay, let us look at the solution, and with a pictorial representation, let me explain you quickly. This is the duct where you have the duct dimension as 80 mm by 80 mm. Okay, and in this you have let us say you consider two sections, section 1 at the entrance and section 2 at a distance 0.3 meter downstream. Okay, so you have two sections, and at these two sections you have to find out what is the difference in pressure. Why there will be a difference of pressure? Because at these two locations we know that there is going to be a change of velocity. Okay, due to the displacement or boundary layer thickness effect, there will be a change in the velocity. If there is a change in the velocity, the effective area where it is going to flow is going to be reduced, and if the area is changing, then if you apply your Bernoulli's equation, you can clearly see that if there is a change in the velocity, there will be a change in the pressure. So we will try to find out from that. Let us look at it. Before I go to the solution, let me explain you a little bit. So here, if you see, these are two boxes I have drawn just to give you a better picture or for visualization. What is going to happen here? As the boundary layer increases from the leading edge of this box towards the inside, you will see the boundary layer will keep on increasing. And we have already seen, assuming that there is no velocity variation within the boundary layer, we can take that there is an apparent increase in the thickness. So what will happen? We can say that at this point the area has reduced, the thickness of the plate has increased, so the area that is available for the flow has been squeezed. And how much it has been squeezed? By the distance displacement thickness from all sides. Okay, so your displacement thickness is given as 1 mm. So the overall dimension has reduced by 1 mm from all sides. Instead of 80 mm by 80 mm, it will become 78 mm by 78 mm effective flow area with a free stream velocity. Okay, so that's the idea. And if you look at this section, something like this will be visible. Okay, the plate thickness would have increased at this point, not practically, but uh, virtually what we are considering. Okay, now let us look at the solution. Apply the, as I said, apply the continuity and Bernoulli's equation to the free stream flow outside the boundary layer displacement thickness, where the viscous effects are negligible. Okay, so with all these concepts we are applying this. Applying this, if you write down the Bernoulli's equation, you can write down at section 1 and 2 both these equations, which we already know. Because viscous effect is negligible, there is no head loss in this. So you could write down P1 by gamma plus V1 square by 2g plus Z1 equals to P2 by gamma plus V2 square by 2g plus Z2. Z is same. They are at the same level. So Z can be taken out. Now what you have is P1, P2, V1, V2 terms. By rearranging that, because we want to find out the pressure P1 minus P2, the change in the pressure, so you can write down P1 minus P2 equals to half rho V2 square minus V1 square. Now V2 square minus V1 square, we can easily represent that using the relation between these two. We can put it using the continuity equation, where A1 V1 equals to A2 V2. So V2 is equals to A2 by A1 multiplied by V1. By substituting this in the Bernoulli's equation, you can write down P1 minus P2 equals to half rho V1 square multiplied by A1 by A2 whole square minus 1. Okay, this is just substituting these values. Now let us look at the solution of this. If we know A1 and A2, we know the value of A1 and we know the value of A2. So A1 is the length, that is 80 mm square, and A2 is the effective flow area at 2, that is L, which is the length minus 2 delta. So each side there will be delta reduction. So length of 80 mm L minus 2 delta, that is 2 mm, is going to give you 78 mm. So by substituting all these values in the above expression, you can straight away get the result, and you will be able to obtain that the drop in the pressure comes out to be 58.75 Pascal or Newton per meter square. Okay, so it is important you understand the whole process and then start applying the concepts, so that you will be able to get the correct result. All right. Okay, so now having understood this, let us understand something more than that, that is called momentum integral equations. Okay, so the Blasius solution of differential equation, that is the boundary layer equations, gives the velocity distribution in a laminar boundary layer. Okay, and from the velocity distributions we know that the parameters like delta x or boundary layer thickness at a distance x, as well as the shear stress at some distance x, can be evaluated, and we can also find out the drag force on a plate. Okay, so in an alternative approach, Kalman integrated the equations of motion over the boundary layer thickness to get some expression like this. Okay, so I am not getting into how these derivations happened, all that, but let us take it forward from here. Kalman integrated this, which is why it is also called von Karman integral momentum integral equation. So von Karman momentum integral equation, for that Kalman integrated this equation of motion and derived tau 0 by rho is equals to d by dx u square theta plus delta star u du by dx. Okay, and in this, if we consider that there is a zero pressure gradient within this boundary layer, then we can say that du by dx is equals to 0, because the boundary layer thickness is very small. If we can assume the based on the Prandtl's approximation. The pressure outside is imposed on the boundary layer. So the pressure gradient is 0. Then that means we consider that du by dx is going to be 0. And with that assumption, we can tell that this term will disappear. What will remain will be this much. Tau 0 by rho is equals to d by dx of u square theta. Okay. So taking this forward, this expression can be arrived by applying continuity and x momentum equation to the differential control volume. We have not gone through the derivations of this equation. Okay. And for that, obviously, we have assumed that the flow is steady, fluid is incompressible, and it's a 2D flow with no body force. Okay. So these are the conditions which needs to be considered, and you apply the continuity equation and the x momentum equation to get that expression. Okay. So the momentum integral equation can be applied to both laminar and turbulent boundary layers. This is the advantage of that. So you can apply this momentum integral equation to both laminar as well as turbulent boundary layers, but in case of Blasius solutions or Prandtl's boundary layer theories, we have only applied or we have only derived up to laminar boundary layer. Okay. So a reasonable velocity profile shape inside the boundary layer can be assumed, which we have seen how a velocity profile assumption can lead to different values of shear stress and drag force and all that. Okay. The wall or the shear stress at the wall is related to the velocity field. So we can apply the Newton's law of viscosity, or we can apply Blasius empirical relationship and find out the values or the shear stress. Okay. Now the boundary layer thickness can be evaluated from an ODE in terms of delta. Okay. And for example, if a laminar boundary layer is considered, we can write down u by u is a function of eta, and we can write down the velocity profile y by delta, u by u variation is 2 eta minus eta square. Okay. So this is a ODE that we are putting it. And with that, we have to also check whether the boundary conditions are applicable or not. We have to check that, which is nothing but y is equals to 0, your u by u is equals to 0, and y equals to 1. Okay. Or y equals to delta. I think it should be y equals to delta. U by u is equals to 1. Okay. So how do we solve it? You find out the tau or tau 0 based on the momentum integral equation and apply the Newton's law of viscosity. Then equate these two expressions, okay, and get the final solution. By solving like this, we could the expression that was arrived at is delta by x equals to 5.48 divided by square root rex, and the CD value, that's the drag coefficient, was obtained as 1.46 divided by square root rex. Okay, the CD value you can obtain once you find out the drag. You know the drag force equals to half CD rho s rho v square, and using that you can find out what is the value of CD. Okay, now if we compare the expression that we obtained based on the Blasius solution, you can see that Blasius solution gave us delta by x is equals to 5 by square root rex and CD equals to 1.328 by square root rex. So with the advancement, we have got different theories, different values could be arrived at, but still the values are still close to the Blasius solution what we have obtained. So in many cases, Blasius solution is widely adopted. All right, now we have seen the laminar boundary layer so far. We have talked about the momentum integral equation. I'll quickly touch upon the turbulent boundary layer, but not the derivations, but to give you the essence of the concepts. So in case of turbulent boundary layer, a suitable velocity profile on a smooth boundary is following 1 by 7th power law, and that expression is given as something like this: u by u is equals to y by delta to the power 1 by 7 or eta to the power 1 by 7. Okay, so with this, the profile we can say that the profile does not hold in the immediate vicinity of the wall. Why? Because we have already said that in the immediate vicinity of the wall there is a laminar sublayer, so it is not turbulent. So this profile or the 1/7 power law is not going to be valid in the immediate vicinity of the wall. At the wall, du by dy is going to be infinity because it is 0. Suddenly it is increasing, so the gradient is substantially high, so it tends towards infinity. Okay, and that's why it is not applicable. And the boundary shear tau 0 cannot be evaluated from the assumed profile that we have shown here. So borrowing an empirical relation or expression from pipe flow that was derived, we have not discussed those things so far, but we can just take it as a concept. Borrowing that expression from the pipe flow where r is equals to delta. So from the midpoint, you have the radius of the pipe, and that we consider as delta, as the boundary layer thickness. Okay, and V average is equals to 0.817 u. Average velocity within the pipe is going to be 0.817 times the free stream velocity that was considered for deriving this expression. Okay, and taking these values for the boundary shear, we can derive the boundary shear and can be written in terms of free stream velocity u and the boundary layer thickness delta. Okay, so we can write down tau 0 at the wall is going to be equals to 0.0233 rho u square nu by u delta to the power 1/4. So this is something which, based on the derivations and so on, we could write down the shear stress at the wall for the turbulent boundary layer. Okay, and by equating the values of tau 0, okay, of the momentum equation, the empirical relation could be arrived at, that is tau 0 by x is equals to 0.382 divided by rex to the power 1/5. Earlier we used to derive delta by x and the expression used to be something else that used to have square root of rex. Now it is rex to the power 1/5, and there is a coefficient. Similarly, coefficient of friction Cf can be derived, which is given here, 0.0594 divided by rex to the power 1/5. So these are the values we could get for the turbulent boundary layer. Similarly, we can also derive the coefficient of drag, which is going to be 0.074 divided by rex to the power 1/5. And this coefficient, drag coefficient, is valid for this range, that is for Re between 5 into 10 to the power 5 to 10 to the power 7. Okay, so if it is beyond that, then there are other expressions. We are not actually getting into those. So overall, what is the essence of this turbulent boundary layer theory? That the thickness of a turbulent boundary layer is much larger than the thickness of a laminar boundary layer. If we solve, we will be able to find out that the thickness of turbulent boundary layer is much larger compared to the thickness of the laminar boundary layer, and the distribution of velocity in turbulent boundary layer is fuller. So if you see this is more flat and only the gradient is seen close to the boundary, whereas if you look at the laminar boundary layer, the overall profile is going to be parabolic. Okay, so we call it more fuller. All right, even in case of turbulent boundary layer, a laminar sublayer is going to exist. We have already discussed that. You have the laminar sublayers very close to the boundary, even in the turbulent boundary layer. So this is very, very important because the wall behaves hydrodynamically smooth or rough. Please understand this word hydrodynamically. The wall could be smooth or rough. We are not worried about that. Whether the hydrodynamic effect is filling the wall as smooth or rough, that depends on the height of the roughness relative to the laminar sublayer thickness. The laminar sublayer thickness below the turbulent boundary layer is going to play and decide whether the wall is going to behave as smooth or rough. Okay, so a roughness height, if there is some undulation in the wall, if that is going to be felt by this laminar sublayer thickness, then it is going to behave as rough. If that is not being felt by the laminar sublayer thickness, then it is going to behave like a smooth wall. And why is it important? Because in the laminar sublayer thickness, you have a very high velocity gradient. Okay, and this very high velocity gradient is going to give you a very high shear stress. All right, so now the shear is very high. Now a small undulation or small roughness can also lead to a large drag force, and then the hydrodynamic behavior, or hydrodynamically the surface is going to be rough. Okay, if it is very small, the roughness height is very small, then it will behave as a smooth surface. So that is why it is very, very important. So finally, the thickness of laminar sublayer decreases with an increase in the Reynolds number. If the flow velocity is going to increase, that means the momentum is going to be dominant, and this thickness of the laminar sublayer will decrease further. Okay. All right. So these are the essence of the turbulent boundary layer. With this, we have come to the end of the solutions of Navier-Stokes equation, where we discussed the exact solutions, approximate solutions. In approximate solutions, we actually discussed boundary layer thickness and various boundary layer theories, which are very, very important concepts of fluid mechanics. All right. And with this, let us stop in this lecture. In the next lecture, I am going to talk about the turbulent flow. Not the boundary layer thickness, but the turbulent flow as such, and that we will take in the next lecture. With this, thank you so much and have a good day.